Hello, welcome back to another episode here of non-commutative geometry and naive class theory. In this one, we're going to introduce a special with an introduction to naive class theory itself. Now, I will warn you, this is going to be mathematically dense, especially as we get deeper into the video, so hold your horses, and hopefully some of you who aren't necessarily into higher math can still gain something from this. So we'll start off with the question, what is naive class theory? So naive class theory, which we call NCT, is an abstraction of the process of mathematics as well as a philosophy of metamathematics as a whole. And so basically it's a combination of multiple things. One, it's a generalization of higher category theory inspired by the frameworks of topos theory, differential geometry, sheaf theory, homotopy theory, functional analysis, quantum field theory, lambda calculus, and various cohomology theories, among other things. Two, it assumes an incoherent background as a prior upon which we project meaning onto what we call a pre-space, whether it be through the imposition of axioms onto a space that features no prior axioms or by enforcing operators such as truncation, inclusion, etc., upon test functions to see what structure or obstructions to structure may arise. It may also be viewed as the study of evaluating, approximating, or postulating the relationships in objects that may emerge from spectral sequence-like processes where abelian and associative structures are not guaranteed. And so, three, in a way, this can be viewed as a generalization of the process of renormalization over quantum field theories. So we generalize that and basically reverse the chain of logic entirely. We start global or non-local, and we have no privileged notion of locality a priori, and then we project towards locality while acknowledging that layers of uncertainty are non-trivial to our notion of incoherence until we reach a terminal category. So let CU be a global ambient space that acts as an incoherent background of pure potential for a mathematical universe, denoted U. This ambient space, which is a sort of pre-space, if you will, is called the universal class. Coherence classes are indexed by epistemic finiteness. So on the furthest left, we have the most localized we can possibly get, which is a terminal class, C0. And on the furthest right, we have the universal class, which is basically the terminal object at the most non-local sense. So localization towards coherence from a universal class is defined by the projection map. So we project onto a universal class to reach a localized coherence class. And so this can be viewed as a surjective map that represents the act of observation or measurement, if you will. Once an initial projection is performed, one can restrict to a specific coherence scale through the act of truncation. So where m is greater than n, the truncation from m to n takes us from the mth coherence class to the nth coherence class. It localizes us further down the ladder here. And so truncation acts as a functor that loses resolution for an increase in epistemic clarity. This is a push forward of sorts. The fundamental derivative is given by a variation operator. So it bumps us up 1 degree in our coherence class, or 1 level in our coherence ladder. And so variation acts as a derivation that nudges us 1 step closer towards incoherence. So essentially, truncation is sort of like a generalized integration, where our variation is a generalized derivation. Inclusion is then a fully faithful functor. It basically does the opposite of what truncation does, in a sense. So inclusion acts as a functor that gains resolution for a decrease in epistemic clarity. This is a pullback, which is dual to a push forward. Enclosure of incoherence is then given by a limit. So the limit of our nth coherence class as n approaches infinity is equal to C infinity, such that the union over all n of our nth coherence class equals the universal class. And then truncation is then argued to be the left adjoint to inclusion. We could have composed a structure where we discuss right adjoints, but nonetheless we choose a left adjoint to simplify things here for this video. This allows us to form units and co-units, respectively. So here's our unit given by eta. So we go from an identity to a composition of inclusion with truncation. But we would have a co-unit in the case where we start with truncation and inclusion, and then go towards an identity in another coherence class. So let omega measure potentiality and lambda measure locality. There then exists an n star such that the potentiality of an n star coherence class is equal to the measurement of that coherence class. And so this is a unique point at which potential gained equals information lost. In a way, you can consider this a generalization of the principle of stationary action. And so epistemological ontological balance is given by the composition of potentiality and locality equaling a constant across n. And so basically this is the point in which the actions that you engage in with epistemology and ontology are effectively indistinguishable. Once again showing more or less a generalization of the principle of stationary action, but in the case of a more higher level logic overall, from which something like that stationary action principle is a relatively local emergent process from this. For any square of indices a less than or greater than b and a prime less than or equal to b prime, the following diagram commutes up to a canonical isomorphism. We're going to draw this square here, starting with a coherence class in terms of b. We can truncate from b to a lower degree a through this truncation operator from b to a to reach a coherence class in terms of a. But then we can also perform inclusion from the non-primes to the primes in this case to then reach the prime coherence classes here. And we can also jump between those prime coherence classes from one to another through another truncation operator, of course in this case from b prime to a prime. And its canonical mate, a Beck-Chevalley two-cell, is the following isomorphism. It's an isomorphism of the commutativity, essentially, of the inclusion and truncation operators. And so altogether, this whole condition is called the Beck-Chevalley condition. And this guarantees coherence across composition and different degrees of grading between indices, essentially across our theory. So it's kind of the condition upon which mathematics can emerge in a coherent way across all coherence classes from the coherence class under projection. And so the variation operator is nilpotent at second order since we have a two-cell that we're respecting an isomorphism under for which the Beck-Chevalley condition holds. So delta squared is equal to 0. This is second order nilpotence. And there is a natural transformation called the Leibniz rule, written in this case in terms of a monoidal product, which essentially generalizes the tensor product. And you can see the variation of objects x cross y mapping to a variation on x cross y with the direct sum of x cross the variation of y. And so this is a generalization of the product rule in calculus. The variation operator is then a strong derivation on a graded monoidal structure. The kth coherence cohomology group is then given by the following, and this should be familiar to anyone who is familiar with, for example, DRAM or Dobolt cohomology. So the kth coherence cohomology group of a coherence class C in terms of a degree n is given by the kernel of variation operator acting on the nth coherence class modulo the image of that same operator acting on n minus 1th coherence class. And so this measures the stability of an act of reasoning and is therefore the space of epistemically conserved quantities. Since the variation operator is not bound to any specific geometry, algebra, or categorical structure, it essentially acts as a meta-derivation across entire coherence levels themselves. So this means that the variation operator governs transformations among epistemic grades of coherence instead of chain complexes in a fixed space. So traditional cohomologies, whether that be de Rham, Dobolt, Sheaf, Hochschild, cyclic, etc., and other cohomologies in general, are all just projections of this scheme when we instantiate coherence classes as specific localized mathematical universes, and such as those formed by, say, manifolds, groups, sheaves, fibers, etc. In this case, the variation and inclusion operators are generalizations of the process of derivation, whereas projection and truncation operators are generalizations of the process of integration. The process of reasoning closes at second order, just as curvature closes under the Bianchi identity, and this holds up to the case where we satisfy this Beck-Chevalley condition as a two-cell. Curvature is then given by the coherence commutator itself. So this principal curvature K is given by the commutator of inclusion and truncation, and that equals the composition of inclusion and truncation minus truncation and inclusion. So now we interpret curvature as a measure of obstruction to global coherence that reproduces incompleteness as a special case. When K is equal to 0, truncation and inclusion commute, which generates flatness. And what we mean by flatness in this more generalized sense is basically a measure of how sensible it is to argue for truth or falsehood as a perfectly binary system. So when K is not equal to 0, truncation and inclusion fail to commute, which generates what we call curvature. And curvature in this general sense means there is not a binary true or false that can be trivially obtained. Rather, we have degrees at which things are partially true and partially false in a dynamic, relativistic, and potentially superpositional sense. Through the Beck-Chevalley condition, K is a curvature two-cell that vanishes under variation, since we are talking about a commutative square, as opposed to, say, something like a commutative cube or some commutative hypercube. So the variation of the curvature two-cell equals 0 in that case. So this means that epistemic curvature is conserved up to a Bianchi identity. So in summary, naive class theory is a differential calculus for prespaces. And these prespaces of potential are structures where associativity, commutativity, even perhaps an identity element, and such things as completeness are not assumed, but rather emergent as the zero curvature limit of a coherently conserved epistemic geometry. Or if not a geometry, just a more epistemic process more generally. So in other words, a prespace is what a category looks like before coherence is induced upon it through projection, for example. It's a raw epistemic manifold, if you will, in which reasoning, composition, and locality are merely these emergent phenomena, not something that are guaranteed a priori. So when curvature vanishes and adjunctions stabilize, which is the case where K is equal to 0 and the Beck-Chevalley cells commute strictly, this prespace, which is the universal class CU, collapses to what we call an abelian category. Thus, all of classical mathematics, whether it be sets, groups, manifolds, categories, topoi, fiber bundles, etc., emerge as flat limits of an epistemic calculus at a higher level. So now we'll consider the commutativity of inclusion and truncation as a special case of categorical equivalence. So here we have inclusion composed with truncation acting on V, which is a profunctor that in this case is a bimodule, and that bimodule acts as a kernel that's acted upon by this inclusion and truncation. And we can expand this in terms of what's called a coend formula. This is the coend, which sort of generalizes integration here. And at the very end here, we see that V, this bimodule, is essentially a generalization of a measure or a differential. And once again, this integral symbol represents a coend, If those indices a and a naught were at the bottom of this integral symbol, we would have what's called an end, and so in this case, ends are to homology what coends are to cohomology. We can split this coend up into two integrals because coend is like a generalization of successive integration in a categorical sense. And this right-hand integral is condensed down into inclusion here, as we see across this monoidal product here, and that's what that tensor product looking thing is here. It's the monoidal product in a more general sense for categories. And basically what we've performed is a commutation between inclusion and truncation. And so here the composition of inclusion with truncation acting on the bimodule, the profunctor, is isomorphic to truncation composed with inclusion acting on that bimodule. So this shows commutativity up to the Beck-Chevalley isomorphism. So this is a two-categorical instance of Fubini's theorem, and then the one categorical shadow of this statement is called the Stokes-Cartan theorem, the all-famous fundamental theorem of calculus in n dimensions, expressing that the integral over a manifold of the exterior derivative of a differential form is equal to the integral over the boundary of that manifold of the differential form itself. Of course, that's just a case where we have smooth manifolds. And so we show here that there are effectively infinitely many higher structures beyond Stokes-Cartan in that manifold analysis. And this process can be extended under commutativity to infinity n categories. And so we no longer care about smoothness, and rather we care about dualities between boundaries and co-boundaries. And that's kind of what the Stokes-Cartan theorem has really been hinting at all along. In other words, when push-forwards and pullbacks commute, the Beck-Chevalley condition expresses a law that integration and differentiation, in a localized sense, commute across all categorical dimensions. The Beck-Chevalley condition in that case can be considered the fundamental theorem of calculus for infinity n categories, making the Stokes-Cartan theorem the fundamental theorem of calculus for 1 categories. And so we can think of the Stokes-Cartan theorem outside the realm of smoothness altogether, like I mentioned before, and focus instead on the duality between boundaries and co-boundaries. This then implies that there are indeed such Stokes-Cartan theorems for fractal, discrete, and even non-commutative spaces as well. For example, the special case for non-commutative manifolds is in fact Kahn's trace theorem, which I have shown in a prior video. Each form of this Stokes-Cartan theorem is a one-categorical shadow of an infinity categorical tower, and we'll get into more of what that higher Stokes-Cartan theorem looks like later on in the video. So now let's manage the known associativity of coherence classes through Hopf-von Neumann algebras. In a prior video, I expressed a construction of a Hopf-von Neumann algebra starting with an arbitrary Lie group capital G and its corresponding Lie algebra lowercase g, which was a tangent space at the identity of G labeled T sub I of G. We were able to express the tensor algebra of a Lie algebra that we denoted T of G, which allowed us to provide associativity through the action of the tensor product. And by quotienting out an ideal from this tensor algebra, we saw that we could define the commutator of the Lie algebra in terms of a difference of tensor products, and this quotient algebra was then recognized as the universal enveloping algebra, T of G / I equals U of G. Through this, we encoded all left invariant differential operators on the Lie group. To obtain the right invariant differential operators, we noted that we could perform the same process as before on the opposite Lie algebra, denoted G-op, to obtain the universal enveloping algebra on the opposite Lie algebra. The tensor product between the universal enveloping algebra of the Lie algebra and the universal enveloping algebra of the opposite Lie algebra allowed us to compose the left and right invariant differential operators as a unified associative algebra that we called A. However, since the centers of both these universal enveloping algebras were isomorphic, we ended up in a situation where Casimir operators, or bi-invariant differential operators, were double counted. To resolve this, we took the bicommutant of the associative algebra to form a subalgebra called a von Neumann algebra, also called a W-star algebra. And we recall that bicommutant expresses the elements of the universal enveloping algebra that commute with the elements that commute. And so this is given by M, which is the bicommutant of the tensor product of these universal enveloping algebras. By assigning a Hopf structure to M through a coproduct delta, an antipode S, and a counit epsilon, we formed an operator bialgebra called a Hopf-von Neumann algebra, given by the quadruple M, delta, S, and epsilon. Our Hopf-von Neumann algebra gives a sense of both associativity and co-associativity to a space of invariant differential operators on a Lie group. And through these very structures, we make sense of what it means for associativity to FEL in a more general sense. So now we'll look at a restricted example of this in a naive class theory. We fix a universal class Cu and choose a universal Hilbert space H sub u to represent this ambient space. A level n Hilbert space is given by choosing a closed subspace within the universal Hilbert space called H sub n, and that's given by isometric inclusion. And that's that operator J sub n here. A property of n here is that the adjoint of J with J gives us the identity in that nth Hilbert space. So truncation at level n is then given by the following projection definition, where E sub n is defined by J sub n with the adjoint of J sub n. So essentially that very thing that gives us the identity in the Hilbert space, we commute that essentially to get truncation itself. And that makes sense because inclusion and truncation are adjoints of each other. And so E squared sub n is equal to E sub n is equal to the adjoint of E sub n. And so a boundary operator is given by the adjoint inclusion, which is given by P sub n. That's defined basically just by J star sub n, the adjoint of J sub n, which maps us from the universal Hilbert space to a level n Hilbert space, a more localized form of the Hilbert space. So then refinements between levels are partial isometries on the universal Hilbert space. So R sub m to n, which is the refinement operator in this case, is defined by J sub n with P sub n, the isometric inclusion, with the act of adjoint inclusion, which is equal to J sub n and J star sub n. So the ambient associative algebra is given by a von Neumann algebra, a W star algebra. That's in terms of these four operators we just defined on the prior slide that we also are still showing above here. The von Neumann algebra is contained within the space of bounded linear operators on the universal Hilbert space in this case. That's what B of H sub u is, the bounded linear operators of the universal Hilbert space. So co-multiplication is defined on each of the four generators of M, giving delta here. And you'll recall that we used this co-multiplication or co-product to turn our von Neumann algebra in the last video into a Hopf structure. It was the first step of doing so anyways. So we have co-associativity since this co-product extends normally to all M. So this delta here maps us from the von Neumann algebra to the weak tensor product between von Neumann algebras. And so delta cross the identity with delta equals the identity cross delta acting on delta. We show commutativity here in this case in a co-associative sense. So now we choose a normal faithful state, sigma, on M that averages coherent contributions across levels. Omega here is our cyclic or separating vector for a von Neumann algebra. And this d mu of n here is our measure, and it's a probability measure over coherence levels themselves. And so note, we ask for left invariance, but we can indeed do the same for right invariance. And normally we would also want to do this as well, so we can get a theory of left and right invariant operators on the Hilbert space. So now we add an antipode on a core. This was our next step of turning a von Neumann algebra into a Hopf-von Neumann algebra. An interesting switch here on our refinement operator is that when we apply the antipode of the refinement operator, it basically does the adjoint behavior. And so the boundary and co-boundary can then be defined as follows. Partial sub n is equal to j star sub n minus j star sub n minus 1. And that partial symbol there is our boundary, partial sub n, that's our boundary, whereas delta sub n is our co-boundary, and that's equal to the adjoint of the boundary. So we can define a global differential whose closure measures associativity. And that's given by the total differential d, which is the sum over all n of the boundary operator, such that k is equal to d squared, or alternatively, instead of defining it in terms of d squared, we can define it in terms of this commutator of the refinement operator. The curvature 2 cell is conserved under variation if and only if composition of operators survive the Beck-Chevalley check. And that is the case where delta composed with E sub n is equal to this product between E sub n with itself, acting then on delta, where keep in mind E sub n squared is equal to E sub n. So this just shows essentially the commutativity between delta and E sub n in this case. So once again, if this condition holds, then curvature, in this case non-associativity itself, vanishes under variation. And so once again, we get back to the condition where the variation of the curvature 2 cell is equal to 0. So this then implies second order nilpotence of the total differential, and we realize in this case that associativity itself is what provides epistemic stability at this level. So nilpotence is at second order because the Beck-Chevalley condition is in respect to a square diagram that commutes. However, if nilpotence was at third order, this would be because the Beck-Chevalley condition is satisfied in respect to a cubic diagram that commutes. So if we move to an n-dimensional coherence, such as with a hypercube diagram, which it would be an n cell and an n category, for example, then nth order nilpotence corresponds to commutativity of that hypercube. So d is nilpotent at order n. That is to say, d to the n equals 0. Our differential, our total differential, vanishes for all n. Closure of a 2 cell gives ordinary associativity. Closure of a 3 cell gives coherence of associativities themselves. And so closure of an n cell corresponds to coherence of epistemology at order n. The infinity n categorical Bianchi identity is now going to be constructed here. Let G, L sub 1, L sub 2, L sub 3, etc. be an L infinity algebra representing the infinitesimal datum of an n group. A higher connection on a space X is a collection of differential forms. So A naught is an element of the space of differential 1 forms crossed with G sub 0. A sub 1 is an element of the space of differential 2 forms on X, cross G sub 1. Likewise for A sub 2, A sub 3, so on and so forth. We just get this general pattern here where A sub k is an element of the space of differential k plus 1 forms on X, cross G sub k. So higher curvature forms f sub 1, f sub 2, etc. are defined by the homotopical Maurer-Cartan expansion. So the n-categorical Bianchi identity is then the following equation, in this case expressed in terms of a covariant derivative since we're using connections here. So the covariant derivative of the curvature form f equals 0. And that's a curvature n form in that case, that f symbol is. So this equation states that curvature at each level is covariantly closed by the next level of coherence. So in terms of naive class theory, the Beck-Chevalley condition holds for the higher case. So the variation of curvature at rank r is equal to 0 for all r that are less than or equal to level n. K1 measures nonlinearity, K2 measures non-associativity, K3 measures failure of coherence between associativities, and onwards. So the infinity n categorical Bianchi identity for naive class theory is yielded by the categorical colimit as r approaches infinity. So that is to say, curvature vanishes at the infinite level. And so coherence is captured all the way across the coherence cohomology, regardless of the categorical dimension that you're concerned with. And so that is d infinity equals 0. It's nilpotent upwards to infinity. As such, the higher Stokes-Cartan theorem for naive class theory states that epistemic flux through a boundary equals epistemic variation of curvature. Therein, both vanish coherently in the universal class up to a canonical isomorphism where the Beck-Chevalley condition is satisfied. This is given by the commutator between truncation and variation. It vanishes up to an isomorphism satisfied by a Beck-Chevalley n cell where the n approaches infinity.